Hello. This is the third time when I'm trying to record this lecture. Uh, Previously, the quality of recording was terrible, so I do it again. So this time we talk about equilibrium, and normally we believe that equilibrium is something in the state where nothing happens. That is not always the case, especially in chemistry. Uh, Imagine the very well-known example. When you take, for example, sugar and add it to water, initially it dissolves, but when you add more and more sugar, uh, at some point it stops to dissolve. Why does it happen? Normally, we see the dissolution process as a process where the molecule of the solid go to the solution. They mix with the solvent and go out of the solid, the piece of this solid. So they mix with the solution, with molecules of solution and go here. So the saturated solution is a solution where no solid goes to the solution. The question is, how do these molecules know that it is the time to stop? That no further dissolution is possible. How do they know? Do they have a brain? Do they have eyes? How do they see that many dissolved molecules are here? They don't. Another example, similar example. They have a liquid which evaporates. The process looks similarly. A molecule escapes from the liquid surface and starts to fly. Finally, that may exit may leave the vessel and go outside. That's what we call the evaporation. And if the vessel is open, all molecules finally will escape and the liquid completely evaporates. The beaker will be empty at some point. However, if you put a lid on a beaker, there will be no full dissolution, right? Some molecules escape, but at some point the vapor above the liquid surface becomes saturated and no further evaporation occurs. How do these molecules know? They cannot evaporate anymore. There are definitely some communication between these molecules, the molecules of vapor, and the molecules of liquid. But how does it occur? The answer is similar. Neither dissolution nor evaporation stops. It's constantly occurring. However, there are two competing processes. First process is evaporation, when the molecule escapes from the liquid, and the second process is condensation, when the molecule which travels freely and randomly may come to the surface and stick to it and leave here. So these two processes are competing. And obviously, the equilibrium in this particular case is the situation when the rate of condensation and rate of evaporation are equal. And this type of equilibrium is called a dynamic equilibrium. So, in other words, this is a state where two processes occur, and these two processes are competing. And when their rates are the same, we can speak about equilibrium. And the rate of these processes may be very, very big. However, we see no changes because they totally compensate each other. Now, the question is, how can we describe the position of this equilibrium, and how can we characterize it? To characterize it, we need to draw an equation. And obviously, the rate of evaporation, VE, can be expressed as follows. This is a probability of a single molecule to evaporate. Let's call it P evaporation, times the number of molecules that are potentially capable of escaping from the liquid. And this number is proportional to the surface area of the liquid, S. We do not care about exact number of molecules, but we know that these molecules are packed densely. So if we know area, we know the relative amount of molecules per square centimeter, for example. What about the second process, the process of condensation? The condensation rate, the speed of condensation, equals to what? The probability of a molecule to come to the surface and to stick. So this is P. C times S, right? If the bigger surface, the bigger probability. But in addition to that, one more parameter should be added here, because the density of vapor is different. It can be different in contrast to the density of liquid. Then the vapor may be dense. That means many molecules are here. That means the probability increases times the number of so we need to add the number of molecules, or number of moles of molecules per 1 liter, or that can be, and this is a partial pressure, the pressure of these molecules if we remove all other molecules, including the air molecules. So when the equilibrium is achieved, these two rates are identical. They are equal. That means we can write an equation as follows. P, the probability of condensation, times area, surface area, equals to probability of evaporation times the probability of condensation, equals to probability of condensation times area times the pressure, vapor pressure. The next obvious step is these two values are identical, so we remove them. And these parameters are the parameters that describe the interaction of this molecule with the neighboring molecule. So that's the property of the material. This is not the property of material. It may be different depending on temperature, whatever, and many other factors. It is convenient to move all parameters that describe the material to one side and the rest to another side. So we get this. PE divided by PT is the probability of evaporation divided by the probability of condensation equal to the partial pressure. Okay. What conclusion can we draw from this formula? The probability of evaporation. What exactly does it mean? To escape from each molecule. Okay, let me make it more realistic. There are more than one layer here. So this probability of an individual. This is the probability of individual molecule. For example, this one to escape. Which factors prevent this molecule from escaping? This is the interaction between their neighbors, between its neighbors. So that means this molecule is supposed to have some threshold energy to break all connections, all bonds, and escape. Obviously, since this energy is the thermal fluctuation energy, which means the higher temperature, the greater fraction of molecules whose thermal fluctuation energy exceeds this threshold. That means this pressure, this probability depends on temperature, and it increases when the temperature increases. With regard to this parameter, it just describes the interactions between these molecules, and that's it. It just describes how strongly this molecule interacts with other molecules. So when the molecule comes, it just sticks. So it is not temperature dependent. So the conclusion is when the temperature increases, this pressure will go up. I mean, the amount of molecules in the gas phase will increase, the vapor density will increase, and finally, when it becomes equal to the atmospheric pressure, the liquid starts to boil. Totally the same formalism can be applied to describe dissolution of solids, because I'm not, imagine this is a solid, and I don't draw the solvent molecules explicitly. So water is here, but we don't show it. So in that case, we also have two competing processes: the process of dissolution, when the molecule goes to solution, and the process of precipitation, when the molecule comes to the surface, sticks to it, and stays. And similarly, we can draw formulas, similar formulas. The dissolution rate equals to the probability of one molecule to dissolve times surface area. And the precipitation rate equals to the probability of a molecule to precipitate times surface area times concentration of this molecule here. How many molecules are here? The actual concentration, that's a standard notation in chemistry, the actual concentration, okay, let's say this compound is, I don't know, I. Let's call this molecule I. So the effective concentration, the actual concentration, is shown in square brackets. you can very frequently find such annotation in majority of textbooks. So that's the actual concentration of molecules at these particular moments of time in this particular solution. And so square brackets has a very specific meaning in chemistry. And again, situation is totally the same. When the solution is saturated, the dissolution rate becomes equal to precipitation rate. So we draw the same equation. These two parameters are equal. So P V times S equal to P T times S times concentration. So we get rid of this, and the equilibrium concentration of this molecule, of this substance, is the ratio between the probability of the molecule to dissolve divided by the probability of the same molecule to precipitate. Let me redraw it here. Probability to dissolve divided by probability to precipitate. This is equal to the concentration, the concentration of the saturated solution. So, as we can see from the comparison of these formulas, two seemingly different processes, such as dissolution and evaporation, are actually described by exactly the same mathematical apparatus. And that is not a coincidence, because there is something deeply common in these two processes. Absolutely the same approach can be applied to a wide range of phenomena, including osmosis, increase of boiling temperature of solutions, decrease of melting temperature of solids, and so on. For example, we all know that during winter, to get rid of ice on pavement of flat surfaces, we use salt. So when we put salt on the icy surface, the ice usually melts. That means that implies that the melting temperature of salty water is supposed to be lower than the melting temperature of pure water. Why does it happen? We can demonstrate it quite easily using absolutely the same formalism. Because melting, there is a deep commonality between melting and dissolution. So here is a solid, and the liquid molecules are kind of more random. They are randomized. So actually, dissolution, melting is similar to dissolution, but the solvent and the solid are composed of the same type molecule. So we have a liquid here and we have a solid here. That means totally the same formalism is applied here. So, but instead of dissolution and precipitation, we can speak about melting and crystallization. Now, imagine that we add some, I don't know, salt here. What does it mean? As we know from this formula, the equilibrium concentration depends on the ratio between dissolution and precipitation, or melting and crystallization. Which process? But when we add dissolved water, salt to the water, what happens to the solvent? The actual concentration of the solvent of water molecule decreases, because what is a normal concentration of water in water? It's easy to calculate. The molecular mass of water is 18. So that means the molarity of water is 1,000 grams divided by 18. It is roughly 55.5 moles of water in 1 liter of water. When we add some additional material to water, when something dissolves in water, the fraction, the molar fraction of dissolved water molecule decreases. That means the concentration of water becomes smaller. But if the concentration of water becomes smaller, then crystallization, the rate of crystallization, the probability that this water molecule will come to the and stick to the surface of the crystal decreases, whereas the probability of melting is not affected. As a result, the melting of ice in the presence of salt is more probable than in the absence of it, and it occurs at lower temperatures than in the absence of water or of salt. Okay, but how all of that is relevant to our problem of the month? I'm not going to give you a direct hint. However, let's think how many other factors may affect these transitions between solid and liquid phase, between liquid phase and vapor, and so on. Does it mean that only surface area, temperature, and similar parameters are the only parameters that affect it? Not exactly. Let's take a look at the geometrical property of the surface of this solid. As I already explained, the equilibrium state depends on two factors: the rate of escape of the molecule and the rate of precipitation or condensation, the probability of that the molecule will come back. However, let's take a look at two specific points here. This is, for example, this is a crystal. If you look at this part, so we have this particular molecule. It is being held by its neighbors, and there are 4, maybe 6, 5 neighbors here. 1, 2, 3, 4, 5. Each of them, that's a 2D example. Obviously, in the 3D case, the situation is different, but nevertheless, obviously, the more molecules surround this particular molecule, the more strongly it is being held in the crystal, and the smaller is the probability for this molecule to escape. And for comparison, let's take a look at this molecule. It is being held by just 3 neighbors. What does it mean? That means that this molecule is much more likely to escape from the crystal, and this point is where another molecule is much less likely to come, because even if it comes, it does not interact really strongly with the rest of the solid. In contrast, this position is very, very good, very, very avidly atomically new returning molecule. That means the edges of the crystal, the vertices of crystal, are the points where molecules are more likely to escape and less likely to return, to precipitate. Now consider one big crystal. So this is a very big crystal, and which means there is effectively no edges here. And some local concentration of the molecules which escape crystal surface forms near this region of the crystal. And now consider a finely ground powder, which is composed of small and very, very small crystals. These crystals actually are pure edges. So molecules are very, very easily escaping from this. That means the local concentration of dissolved molecules are much bigger near finely divided material rather than bulk solid. And now let's see. That means if we have I don't know, 2 bags, a beaker with 2 bags. In one bag, this is a big. This is a water permeable bag. It's not a bag. It's not. It contains lots of holes. And this bag contains fine powder of some material, and this bag contains big crystals of the same material, and all of that covered with a saturated solution of the same substance. What does it mean? The concentration of dissolved molecules here will be slightly bigger than here, and concentration of molecules here will be even slightly smaller than here. That means we have a kind of a gradient of concentration where dissolved molecules will migrate here. So this is not a true equilibrium. The true equilibrium will be achieved when that sounds like a hint. I'm not going to continue. Let me switch to the liquid case, because liquids they have no shape, no specific shape, in contrast to solids. The shape of the surface can be variable. The liquid may form a droplet like this, or when the liquid fills a capillary and fine the thin tube, it may form the shape of the surface is like this. So this surface is convex, this surface is concave, and the curvature, that means the curvature of the surface may vary in wide limits. What does it mean? When the surface is concave, each molecule on the surface has a relatively small number of neighbors. When the surface is convex, the molecule this molecule has a bigger number of neighbors. Which molecule is more likely to escape? This or that? I believe the answer is obvious. This molecule is more likely to escape. This molecule is more likely to come. Now, let's imagine all of that is in some container. This container is closed, and the system is supposed to be at equilibrium. So there is the vapor here, the vapor pressure here is equilibrium pressure. But is it a true equilibrium? No, because the local pressure above these droplets is somewhat bigger because these molecules are more likely to escape. The local pressure above this surface is smaller because these molecules are less likely to escape and more likely to come back. What does it mean? That means when the molecule escapes from here, that ultimately comes here and sticks to the surface. And finally, that situation will end when all molecules leave the droplet and fill the tube. More interestingly, the situation is exacerbated by the fact that when the size of the droplet decreases, when the droplet shrinks, the radius of curvature becomes smaller and smaller, which means the surface is less and less flat, which means the molecules are more and more likely to evaporate. And by the way, that is why in moist air, even when the humidity is not 100%, so it's far from equilibrium, your clothes, you may feel your clothes is somewhat wet, despite the fact that there is no dew on that surface. I believe from that you can understand this. Why does it happen? Practically. One more specific case, and it relates to solids, especially to ionic compounds. So, ionic compounds, for example, sodium chloride, are the compounds where atoms, for example, sodium chloride atoms, are electrically charged. Sodium atom donates its own outer electron to chlorine. Chlorine takes its electron, it completes its outer shell, so the sodium becomes positively charged, chlorine becomes negatively charged. And these positive and negative ions attract each other due to Coulomb forces. So the crystal lattice, I'm showing the 2D example, but the 3D is a bit different, but the principle is obvious. The crystal lattice is looks like this. Each sodium atom, okay, this is sodium, this is chlorine. Each sodium atom is surrounded by chlorine, negatively charged chlorine. Each negatively charged chlorine is surrounded by positively charged sodium. And so there are attraction forces between oppositely charged molecules and repulsion forces between similar molecules. So each sodium repel each other, each chlorine repel each other, but chlorine attracts sodium, sodium attracts chlorine, and you have this type lattice. And the dissolution of this type molecules occurs, this lattice is really stable. However, it dissolves. The sodium chloride dissolves in water, dissolves easily, but not because this compound is not stable. It happens because the interaction of sodium and chlorine ions with water is as strong as interaction of each of those ions with each other. It's not as it's not correct to say. It's incorrect to say that a single water molecule, which is a dipole, interacts more strongly with sodium, with chlorine or with sodium than chlorine and sodium itself. No, but there are many water molecules in solution. So when many water molecules, 10 or more molecules, surround a single ion, this interaction is really strong. And that is why the ion can go to solution. These sodium also charges, and water binds to it with the opposite side, with the negative side. And so due to the dipolar nature of water, it interacts equally well with both positive and negative ions. And that is why ions dissolve. Ionic compounds dissolve. Similarly to other solids, precipitation of the equilibrium is achieved when the precipitation rate and dissolution rate are the same. But how can we describe this equilibrium? The formalism is a little bit different. The formalism is the same for salvation, for dissolution, because it's just an individual interaction between a single ion and water. But precipitation is described using somewhat different approach, because imagine this is a positively charged ion. It comes here, as it brings a positive charge with it. That means the crystal as whole becomes more positively charged. That means the probability of another sodium is affected by that. To make precipitation fast, chlorine ion is supposed to come. Only after that, next sodium can come here. To maintain the overall charge of the crystal neutral. That means the precipitation rate of ionic compounds of salt equals to the probability of individual molecule to precipitate times surface area times the equilibrium concentration of the sodium ion and times equilibrium concentration of chlorine ion. The same, the rest is the same. So that means in our final equation should look like that. The probability of precipitation divided by probability of dispersion equals to, so as you remember, we get rid of that, equals to this. The product of concentrations of both ions. This product is the way, and this and these are parameters that describe the compound, the interaction of these compounds with water. So this parameter, this does not depend on the amount of salt, amount of water, whatever. So that's a constant. That's a property of matter. That means this product is also property, the property of sodium chloride. And you can find it in any text, in every handbook. And this is a parameter. And this parameter, again, is called the solubility product. Solubility product. Obviously, the lower, the smaller this quantity, this parameter, the less soluble the ionic compound is. For example, for low soluble compounds, the BG products may amount to 10 to the power of negative 10, 10 to the power of negative 12, 20, and so on. What does it mean? What does it mean? There are several practical aspects of that. One aspect is as follows. Imagine we have sodium chloride, and this sodium chloride is this solid is at equilibrium with its saturated solution. So there is an equilibrium here. So this is a solid, and the sodium chloride solution is here. Nothing happens. Now we decided to add, for example, potassium chloride here, the solution of potassium chloride, or additional potassium chloride solid. Will it have any effect on this crystal? If you look at this equation, the answer is obvious. There will be some effect, because potassium chloride, it also dissociates in solution to form potassium ion and chlorine ion. That means the concentration of chlorine ion goes up, but this is a constant. This product is constant, which means to compensate that increase, some additional amount of sodium ion is supposed to precipitate. But they cannot precipitate without chlorine. So chlorine will also add here. That means addition of potassium chloride to the saturated solution of sodium chloride will lead to a precipitation of sodium chloride. And that directly follows from that method. Next example. Imagine we have Okay, let's forget about sodium chloride and the potassium chloride. Let's discuss some low soluble compounds like, I don't know, barium sulfate, which is a very, very low solubility, or barium carbonate. So, low solubility of barium sulfate implies that, okay, this is barium, and this is the sulfate. A low solubility of barium sulfate implies that there's just few ions in the solution at equilibrium. Now imagine we add some, and we know that another compound, barium carbonate, is also low soluble. Okay, this is carbonate. And now we add some other soluble carbonate to the solution. For example, sodium carbonate. What does it mean? This compound is this washing soda. It is soluble, and by addition of sodium carbonate to the solution, we bring a large amount of carbonate ions here. But when the carbonate ions come here, I don't draw sodium because sodium we are not interested in sodium. Sodium stays always in solution. It is not participating in precipitation. So I'm not going to show it. We imply it is somewhere here, but we don't draw it explicitly. So what happens when the carbonate meets barium? They precipitate. But solubility product of barium carbonate is lower than solubility product of barium sulfate, which means carbonate, this couple is not prone to go to a solution anymore. Instead, these ions will go to a solution. But if you have a large amount of carbonate here, they are likely to meet with barium and will precipitate again. But this process is not stopped by that. These ions also can continue to come to a solution and meet the carbonate and precipitate. And so on and so forth. What does it mean? What practical implication does it have? It means due to the exchange will constantly occur between barium sulfate and barium carbonate, despite the fact that both of them are extremely low soluble compounds. When we add barium sulfate in the beaker with sodium carbonate, sooner or later, due to equilibration of these two compounds, the barium sulfate will finally become barium carbonate, and all the sulfate comes to a solution. That is an example of what happens when the equilibrium is dynamic. And this is the demonstration that even we don't see any processes to occur, they still may take place. I believe I told too much because it may be very easy for you to solve problem this month, problems of the month. So I may be criticized by our POM committee, so I cannot tell anymore. Good luck with your solutions. And by the way, the announcement of solutions will be done online in the form of Zoom conference, and the announcement. Look at the announcement on our website. Good luck, guys. See you.